Hey everyone, and welcome to section 8.1. We're starting off our chapter about roots and radicals. So we're going to have to remind ourselves a little bit, what do we mean when we talk about roots of a number? Let's remember now, the square root of a number, a, is any number b, so that when I square b, I get a. There's a couple different notational things to be aware of. We have b is equal to the root of a. That is the principal or positive square root of a. And the other one is the negative square root of a. We can define an nth root of a number similarly to how we define a square root. Namely, if you want to know what the nth root of a number a is, it's a number so that when I raise it to the nth power, I get a. That number is the index of the root. So some vocabulary. Radical as an adjective, not generally the same as it is often used in our political climate. Here it's referring to its kind of biological origins. That is, it's anything that is relating to or proceeding from a root. And so that's why the name radical makes sense as a descriptor for root, because it's kind of the adjective analog of root. So when mathematicians were naming this stuff, they're kind of keeping in theme. And then when we talk about a radical as a noun, we generally are referring to a particular expression which is encapsulated by a radical symbol. And a radical symbol is one of these guys. So to get a feel for nth roots, let's make a chart. All right, we know how squares of numbers go. Let's look at some cubes. So the cube of -5 is -125. Cube of -4 is -64, and so on like that. When we cube a number, a variable x, we get x to the third. If we cube the quantity x squared, remember cubing is you're multiplying the number by itself 3 times. So this would be x squared times x squared times x squared, which would be x to the 6th. And from properties of exponents, we know that we're going to be multiplying the exponents together. For the 4th power, we have these guys. And for the 5th power, we have those. So something we want to notice here. For negative numbers, the odd powers are also negative. That's because negative times negative times negative would be positive times a negative, which is negative. So every time you have an odd exponent, your answer is still negative if it was to start with. If it's an even exponent, like a square or a 4th power or a 6th power, your answer is positive no matter what. But this kind of puts some restrictions on what kinds of numbers can have nth roots. For example, we know we don't have real numbers that are square roots of negative numbers, because every time we square a real number, we get something that's non-negative. For cubing, that's not a problem, but for 4th power, we run into the same issue. That is, whenever we raise a number to the 4th power, we get something that's non-negative. There are no 4th roots of negative numbers that are real. So what does this tell us? When we have the index of the root, n, being even, if the number inside of the radical symbol is greater than or equal to 0, we get a real number. But if it's less than 0, if it's negative, then we don't. So we can't take the square root of a negative number, 4th root of a negative number, 6th root of a negative number, and so on. When the root's index is odd, anything goes. It can be positive or negative. You'll always get a real number back. All right, now we're going to be working over the course of the chapter with these radical expressions. So we're going to need a nice way of canceling, so to speak, a radical. It's not quite as straightforward as that, as we'll see. So here we have a few different situations. Up here, we are looking at the fourth root of -3 to the fourth power. Well, this is equal to the fourth root of 81. And again, that symbol in particular is referring to the principal root. So this is equal to 3. And if we look at the fourth root of 3 to the 4, we get the same thing. But when it comes to the odd index roots, that's these guys over here, 3 to the third is 27, and we want the third root of that, we get 3. Meanwhile, -3 to the third is -27. And we can take the cube root of that, which is -3. So this is somewhat significant because notice in the even index case, when the number was negative and being raised to the fourth power, the final answer ended up positive. It ended up as a different sign than it was to start with. But if we look at what happened with the odd index root, we always got exactly what we put in. When we took 3, raised it to the third power, and then put it in the cube root, we got 3 back. Same thing with -3. It's only when I put a negative number to an even power and take an even root that I get something that's different than what I started with. So there's a lesson here. If you're looking to kind of cancel, so to speak, radicals, you need to be aware of this. When you take the nth root of a to the n, it is equal to a whenever n is odd. That's just full stop. You always get back a. However, when you take the nth root of a to the n and n is even, you are really getting the absolute value of a, because whatever comes out is non-negative. So that's something we need to be aware of. And when we simplify radical expressions that have variables in them, it becomes important. All right, so we're going to simplify each expression. We're taking the square root of x squared. It's going to be the absolute value of x, because this is an even index root. So when I quote-unquote cancel using the square root, I'm always getting something that's non-negative. However, for the second one, we just get n. No absolute value signs are necessary. Over here, for the fourth root of p to the 4, since it's even, we're getting absolute value signs. Here we're taking the square root of x to the 6th. So it's worth noting here, third squared. So now we have the square root of something squared. We need an absolute value. And we write our answer. This last guy here is equal to the square root of y to the 8th squared. So it ends up being the absolute value of y to the 8th. However, y to the 8th being an even power is always non-negative, so actually the absolute values aren't necessary, but they don't hurt anything. So let's keep on moving. I have the third root of y to the 18th. This is really like we're taking the third root of y to the 6th cubed. So we get y to the 6th. Fourth root of z to the 8th. It's really like we're taking the fourth root of z to the 4th. Z squared to the 4th power, or absolute value of z squared. But again, in this particular situation, the absolute value sign is not doing anything because the square of z is always going to be non-negative. It doesn't hurt to have it, but all right. And then next up, we're taking the fifth root of c to the 20. This is like taking the fifth root of c to the 4th power raised to the 5th power, because 4 times 5 is 20. So altogether, this is c to the 4th. It was an odd root, so I don't need absolute value signs. Next up, we're taking the square root of 16n squared And this expression inside the radical is a perfect square, right? If we square 4n, we get 16n squared. So I can simplify, however, I need an absolute value sign on my n, because it's a variable. Lastly here, I am taking the negative square root of 100p squared. Similar to the other situation, 100p squared is a perfect square. So we'll have negative 10 times the absolute value of p. So that's just for warm-up. Let's get into something a little bit more intense. Here we have the square root of 36x squared y squared. We want to be imagining this as 6xy squared. And so the xy part is going to have to stay in absolute values because we have an even index root. All right, and let's see here. This expression under the radical is also a perfect square. So when we simplify it after writing it as a square, we're going to get 11 a cubed b to the fourth. The a needs to be surrounded with absolute values because we're using an even index root. We could put them around b also, but b is being raised to the fourth power, so it will always be non-negative. Next up, we're taking the cube root of 8x to the 30th, y to the 12th. Since we know that our rule of exponents tells us we multiply when we raise powers to powers, if we want to kind of bring out a power, we more or less divide exponents. So we end up with 2x to the 10, y to the fourth. No absolute values are necessary because it's odd index. Finally, the cube root of 27w to the 36, z to the 15 reduces to 3w to the 12th, z to the 5th. And we can leave it exactly like that. Right now, that's kind of the intro stuff. What we'll be focusing on next is simplifying some more intense looking expressions.